Welcome back, further students. In this video, we're going to go through how you can use matrices, to solve simultaneous linear equations. Now, you might remember from perhaps back in like year 10 maths, setting up simultaneous equations and solving them using maybe the elimination method or the substitution method. In further maths, in this topic, all you have to know is how to use matrices to solve simultaneous equations. So the key idea here is that you can take a set of linear equations and rewrite them in matrix form, as long as, and there's a couple of things to watch for, as long as each equation has got the variables in the same order. So like you've got your x term first and then the y term second, which is what is happening in both of these equations. And obviously they also need to be set up so that they're, something x plus something y equals a number, right? So the equations have to be set up the same way first, but then once they are, we can represent them in matrix form. And this works, this example here is with just two equations, but this works if you've got a set of 3 or 4 or 5 simultaneous equations, it works the same way. So in this first example, we're actually going to kind of demonstrate why this works, and we're going to use matrix multiplication to show that the matrix equation here, so this is an equation written in matrix form, generates the following pair of simultaneous linear equations. So we're just really trying to show that if we had these linear equations, we could write them as this particular matrix equation. Now remember that when you're multiplying matrices, we go across the rows of the first matrix and down the columns of the second, down the columns of the second matrix. So if we were multiplying, I'll write it again, 4, 2, 3, 2 times x, y. So let's just think about this part of it as a matrix equation. We would get, the first element would be 4 times x plus 2 times y, because remember we're going to cross that row down that column, so plus 2 times y. And when we go to the second row in the first column, we would have 3 times x plus 2 times y. Right, and all of that is equal to, according to this matrix equation, the column matrix 5, 2. Right, so if we have two matrices on either side of an equal sign where we've just got, well, they're both 2 by 1 matrices, right? This has got one element, this has got, this has got 2 elements, this has got 2 elements. We can actually say, well, this would mean that 4x plus 2y has to equal the number 5, and 3x plus 2y has to equal the number 2, because they're just in corresponding positions in these matrices. And that was actually what we were asked to show, right? That these two simultaneous equations are actually represented in this matrix equation. Okay, so that's a bit of an example that shows why this works, why we can set them up the way that we do. Let's have a look now at, once you have matrices or a matrix equation set up, how you can actually solve that matrix equation to find, x equals this number and y equals that number, because that's what you're trying to do when you solve simultaneous equations. So we say that if we've got a matrix equation in the form ax equals b, then the solution to that matrix equation will be x equals A inverse times b. It's not exactly the same, but it's a little bit like the way that when we solve an equation, so if you had an equation in algebra to solve, say, and it was like, I'll write a different color. If you had to solve the equation, let's say 2x equals 10, you would divide both sides of that equation by 2 to get x equals 5. It's a little bit like that idea. Not completely the same, but a little bit like that, right? So it's kind of like we're using the inverse operation, which we actually are using the inverse matrix to solve this equation. So for example, if you had this matrix here, this matrix equation here, this matrix would, the first matrix would be the position of A. This would be the matrix that we're calling X, and this one's the one we're calling B, right? And then you can see that we've rearranged this to say that the matrix X would equal A inverse times the matrix B, right? So that's how this works when we go to solve these equations, and then you actually calculate the result of this inverse times by this matrix B. All right, let's put it into practice and see how it all works. So solve the following set of simultaneous linear equations using matrix methods. And it's really important that if it says using matrix methods, you've actually got to use matrices. So you can't go ahead and solve this with some other method. You've got to put them into matrices. So setting up a matrix equation first, all right, let's check. We've got 4x plus 5y equals 6, 2x plus 3y equals 4. So all the variables are in the same order in both equations. So we can go straight to putting these into a matrix. All right, the variables here are x and y in that order. So it's x, y, and the other side of the equation is going to be the column matrix 6, 4. All right, so there's our matrix equation set up. Now, we said before that if your matrix equation is in the form A times x equals b, then the solution will be x equals A inverse, so 4, 5, 2, 3, the power of -1 multiplied by b. and the matrix B is just 6, 4. Now, even though we're going to get our calculator to do this, it's important that you show that step, right? This is showing that you're solving using the method that was specified, right? And so, new line, let's say xy equals. Right, so we're going to just put this right-hand side into our calculator and see what comes out. So, oops, not 44, 4, 5, 2, 3, power of negative 1, multiplied by matrix 6, 4, we get negative 1, positive 2. Right, now we're not quite done. Don't fall into this trap, because the question was saying to solve the set of simultaneous linear equations, and the solution is x equals this number, y equals this number. So you actually have to take this answer and say, I know what this answer represents is that the x number is negative 1, and the y value, or the y number that solves the equation, is 2. It seems dumb, but you do have to do that step, otherwise you're going to lose a mark. Okay, so take your answer the question basically, don't leave the results in the matrices, always put your answer to the question at the end. All right, there's a couple of things that we've also got to consider when it comes to solving simultaneous equations, and that is that there's not always going to be a solution. And the way that we can look for that or identify these situations is if the determinant of A equals 0. Because if the determinant of A equals 0, we won't be able to calculate the inverse of A, which means you can't solve the matrix equation. In these cases, so if you do have a situation where the determinant of A is equal to 0, what it means is you've either got two equations that are inconsistent, so there's no solution, and they might be two equations where, if you actually thought of them as linear graphs, they would be parallel lines that never cross, right? So they never have a common point where we actually get a solution. An example of that would be 2x plus 3y equals 12 and 2x plus 3y equals 5. Right? There's no, those two things would give you parallel lines and they would never cross over. And if you just look at the equations, it kind of makes sense that there's no way you can put in the same x number and y number, but one of them is going to give you 12 and the other one's going to give you 5. The other situation that's possible is that you can have dependent equations, which means there's actually infinite solutions because you've really got the same equation written twice, right? And if you're trying to solve simultaneous equations when both equations are the same, then every single point along the line is going to be a solution. So we say there's infinite solutions, but there's not one unique solution in this case. So in example 3 here, we're being asked to solve the following set of simultaneous linear equations, again using matrix methods. So we're going to have to set up a matrix equation. We've got to interpret our solution. Now you can probably guess that it's going to be one of these two cases because we've just talked about it, but let's pretend we don't know that. And we're going to say, all right, our matrix equation would be 2, 3, 6, 9 times xy equals 8, 30. Right, and then therefore, so again, that's in the form ax equals b. When we solve it, we would say x equals a inverse times b. Now we can put that into our calculator if we wanted to, but we could also look at the matrix here that we're trying to find the inverse of. Remember that if the determinant equals 0, we'll get no solution. So 2 times 9 is 18, 6 times 3 is 18, so we would get 18 take away 18. So I could actually say that the determinant of 2, 3, 6, 9 actually equals 0, and therefore we've got no solution. Or I should say, no unique solution. Right, so there's no answer that's like x equals this number, y equals this number, and that solves the equation. When we look back at the original equations, one thing that we can look for, and this is, in most cases you don't have to go this far, but it's good to understand it. If I took this first equation and I multiplied everything by 3, right, so I'm going to take this entire first equation and multiply both sides of it by 3, I would get 6x plus 9y, which is the same as the second equation, equals, and 8 times 3 is 24. All right, so if I've got one equation telling me 6x plus 9y equals 24, but another equation telling me 6x plus 9y equals 30, well, I've got the same x and y coefficients, but a different constant, which actually means these two graphs are never going to have a solution. It's actually this situation here, where if you drew them on a Cartesian plane, you'd have two parallel lines that never cross. And so from this, we can actually say that the equations are inconsistent, which means there is no solution. Okay, so that's the sort of thing we're looking for. If we went to put this into our calculator, we'd get something undefined, we'd get some issue. And it's because the inverse is undefined, the determinant equals 0, there's no unique solution, right? And it's because the equations are, or the interpretation is that the equations are inconsistent. Alrighty, one more example to have a look at, and this is a a worded question, and often in simultaneous equations you'll have to set things up from worded information first. So we've got, just to confuse you, we've got a lot of alliteration going on here. We've got Mike, Max, and Manny going to a supermarket together. Can't do that these days, but anyway, only one of them should go, but that's okay. Mike buys 3 apples and 2 bananas for $6.20. Max buys 1 apple, 4 bananas, and a carrot for $6.90. Manny buys 2 apples and 5 carrots for $13. And we're going to let A represent the cost of a single apple, B the cost of a single banana, and C the cost of a single carrot. First job is to write down 3 equations to represent the scenario. So let's start with Mike. Right, so Mike bought 3 apples and 2 bananas for $6.20. So he bought, his order would have been 3 lots of A, whatever A costs, whatever an apple costs, plus 2 lots of B. He didn't buy any carrots, right? And that was all equal to, what was Max's order for $6.20? So 6.2. Max bought 1 apple, so 1A, 4 bananas, and 1 carrot, so 1C, and that equals $6.90. So you can put the 0 at the end, but you don't really have to. 6.9 is the same as 6.90. And then Manny came along and he bought 2 apples and 5 carrots. So no bananas here, but 5 carrots for $13. Right, now our job is to try to work out what each of these things costs individually. So we're trying to solve for A, B, and C. Now, I've kind of tried to leave some gaps in these equations, and you're going to see why when we go to set this up as a system of simultaneous equations in matrix form, or as a matrix equation, because when we put our numbers in, and this time it's 3 equations with 3 unknowns, the unknowns will be A, B, and C. All right, but it's really important that we put zeros in places where there were no values. So it was 3A plus 2B plus 0C. So 3, 2, and 0. The second equation was 1A, 4B, 1C, so that's 1, 4, 1. And the third equation was 2A plus 0B plus 5C. Okay, so that's the left-hand side of our equation set up. The right-hand side are the constants at the end of the equation, 6.2, 6.9, and 13. Solve the matrix equation and hence determine the values of A, B, and C. So again, it's a good idea to show a working step, even though we're going to put all this in our calculator. So remember that this matrix will equal the inverse of A times B. So it's 3, 2, 0, 1, 4, 1, 2, 0, 5, to the power of negative 1. All right, so we're going to put this into our calculator, see what it equals. Whoops, not with that symbol. All right, now it's definitely a good idea, as you're going looking through these examples, to have your calculator handy and do these yourself, because it's one thing to watch someone else do it, but you need to know how to do it quickly and accurately for when you do a SAC and the exam at the end of the year. 6.2. Alrighty, and as you can see there, we get 1.5, 0.85, and 2. Right, but again, we answer the question, right, because we need to actually identify that A is equal to 1.5. And in fact, since that's a cost, let's write that as $1.50. B, which was the cost of banana, is 0.85, so $0.85. And C was the cost of a carrot, expensive carrots, they're $2 each. Alrighty, now there is a little section at the end of this with some exam questions, but I might do that in a separate video because I think this one's already long enough. Hope that gives you a good idea of how to use matrices to solve simultaneous equations, and good luck and have fun with exercise 12B.